Thanks for joining the second week of this webinar series. Uh, like last week, we discussed about valve flow coefficient (CV) and flow characteristics, and this week we'll be discussing hydrodynamic torque coefficient, and consecutive next week it will be cavitation index prediction. So even if you missed the first week, we have some recaps to catch up, so that will help you to catch up and bring it on the same page. Okay, so I'll start with introducing the speakers. Myself, Praveen. I'm the product manager at Simulation Hub. So I'm basically a mechanical engineer with around 15 plus years of experience in CFD applied to different fields, including valves and building HVAC, a lot of simulations. So recently I moved to product management role and then slowly into the marketing role as well. So with me today, I have Akshay. Akshay is our young budding leader. He's the business manager of AVC. AVC is Autonomous Valve CFD. That particular product, he's the business manager. And again, he's a simulation expert and he's very good at client customer relationship. And he handles a lot of interactions and resolves queries of customers, and he's an overall full package. So yes, without further ado, we'll start with the agenda. So we'll start with the recap of week one, as I said. So this will help you to catch up in case if you missed the week one. And then we'll move to we'll introduce hydrodynamic torque coefficient. How do you calculate hydrodynamic torque coefficient? What are the different methods, including flow measurement methods, analytical and numerical methods? And then we'll introduce the application, Autonomous Valve CFD. We'll show a demonstration and case study using the app. So we'll take a butterfly valve for our case study, and then we'll see how the valve trim design, the flow direction, and the valve installation or orientation will affect the torque curve. And then we'll see some real life success stories, how the companies like organizations have utilized the app and applied in real life cases. And then at the end, we'll have a Q&A session. So in case you have any questions or anything, type it in the chat window. I will address them all together at the end. Okay. So starting with the recap, last week we started the webinar with a few real life cases or situation scenarios where we explained, how an undersized valve created a lot of problems of the valve in the valve life, as well as it risked the other equipments in the system, right? And then how the accuracy is equal to money. So how even a small percentage of error in flow measurement will cause financial loss and things. So then we moved on to CV. What is CV and how it is calculated in different methods and formulas, and then how it affects the flow characteristics, and what is the importance of CV, why we need, like what is quick opening, linear and equal percentage. So these things we discussed. And then we went into the app. So what are the inputs required for the app, and what are the process it does in the backend, and what are the outputs, different outputs the app provides. So with that, we moved into a case study. So we took a globe valve case where we modified the plug profile, and we saw, how the plug profile different, like impacted the flow characteristics, CV flow, CV curve. Okay. So with that, now the session, second week session starts. So hydrodynamic torque. Uh, Hydrodynamic torque is more applicable and relevant to quarter turn valves. So valve torque before hydrodynamic torque. Valve torque is the turning effort needed to rotate the disc or ball or plug, the closure member. Okay. So it needed to rotate, the efforts needed to rotate or hold it in some position. So that is the valve torque. And if like it can be, the torque is kind of some extra energy, right? So that is required to overcome certain more forces or energy. So that is based categorized into two things. One is like friction based resistance and dynamically generated resistance. So that extra energy like torque is required to overcome this resistance. Okay. So friction based resistance is when the closure member or the rotating member is comes in contact with the other parts of the valve, so like seating, packing, packing and hub seal, and bearing friction torque. So these comes under the friction-based category. And the other one is because of the flow induced things. So due to the liquid, okay, liquid that is liquid. So hydrodynamic torque and hydrostatic torque, weight and center of gravity torque. So a lot of things. So today's focus will be more on the hydrodynamic torque. So hydrodynamic torque is the turning moment purely due to the fluid forces around the closure member or rotating body. Okay, so let's take the case of a butterfly valve. So where you can see the disc is at some partial opening, and then the flow is from the left to right. So because due to the flow, there are pressure forces and liquid forces acting around the turning disc, the rotating disc. Especially the leading and trailing edge of the disc experiences different velocity as well as the pressure. So this imbalance in the pressure causes a turning moment. So that is to overcome that experience, like, that tends to close the disc. Okay, so that is like closing top. So that is to overcome that we take help of the actuator. You can see in this right side image. So now we are introducing hydrodynamic torque coefficient. Hydrodynamic torque coefficient is nothing but it's a non-dimensional representation of dynamic torque. It is calculated using this formula. You use the dynamic torque divided by pressure drop across the valve and multiplied by the diameter of the valve Q. So a typical CDT, the dynamic torque coefficient is represented as CDT. The CDT curve looks like this, a typical CDT curve. It varies. We'll see those things in the further slides. So for every opening, we calculate CDT and we provide it. So once this CDT is available, you can calculate the torque, dynamic torque specifically required for any pressure drop or any flow conditions. Okay, that's the idea. So it's a non-dimensional representation. So the torque varies according to the pressure drop across the valve, the total dynamic torque. So that the CDT remains constant. Okay. So CDT is a non-dimensional number. It is calculated for each and every angle of opening, and that remains constant for any flow conditions. And that can be used to calculate the actual dynamic torque for your operating condition. So what are the factors that affect CDT? So there are many factors. So we'll see one by one. So first, to start with, the valve opening. So the valve opening, we saw that will impact the CDT value, okay, and the pattern of curve as well. And the valve size affects the CDT values and the curve. So you can see as the size increases, the CDT value increases, and the impact of hydrodynamic torque on the total torque or actuator sizing, that is more in the as we go for the higher sizes. Okay, and then again the valve type and the design will also define the pattern of the curve. You'll see even within a type, valve type like butterfly valve. Again, symmetrical butterfly valve has a different type, and then offset valves will have a different type of curve. So again, the pressure drop. This will not affect the CDT per se, but the torque value. how the pressure force is acting on the surface of the valve or the rotating member, that will have an impact on the value of dynamic torque. And then the flow direction, as I said, the offset valves. So even within offset valves, let's say you orient the offset valve such that the seat retainer is in the upstream. It is facing the upstream flow direction. Then it will have the red. You can see the red curve. It will have a different curve, the which goes from CDT value goes from positive to negative value. And for seat downstream, it is like this. At even at 90 degree, there will be a slight, uh, you know, value of CDT you will experience. Okay. So in symmetric valve, it is more towards nearly zero, but in offset valves, it will have some value. And coming back to seat upstream case, where it changes the a value from positive to negative. So what positive indicates is the forces tend to close the valve, and negative indicates the forces tends to open. So in between where it crosses the zero, like zero line, the x-axis, so that is torque reversal point. One tends to like we need to avoid uh, operating in this opening, okay, where the torque reversal is found. So the next comes again, it's a valve installation or orientation related impact like factor. The flow profile at the valve entry. So because of the bend, the valve is installed near the bend, and because of the flow profile, because of the bend, it will experience a different pressure profile and pressure force on the disc, and that will have a big impact. We'll see some cases. So this is one of the cases. Like last factor, I pulled out from some references from Bray document. How to install in different cases at the discharge of a pump, downstream of a bend, and combination of different valves. So how do you install it? So which one will be more effective or recommended way, and which one we should avoid? Okay, so there are two orientations. One is the stem is perpendicular to the bend and flow direction, and the other one is like the stem is vertical. Okay, it's parallel kind of flow. So that we'll see, this orientation will be more beneficial than the other one. So here the torque reversal and other things will happen. We'll have a detailed case study at the end. Akshay will run through those case studies and you'll understand why this is the recommended thing. So here it's very simple. I'll take the case of a bend. So in the previous slide, we saw the flow profile, exposed to the disc will be non-uniform. Okay, so in this case, it is better when the stem is vertically placed, and then both the sides of the disc surface will have, better flow profile faced by the disc. So that's the reason this is recommended. And how jumping on to the next thing. So when we have the CDT curve, how it is used to do the actuator sizing. So one disclaimer. This is not the intent of this webinar, actuator sizing, but I just wanted to extend the topic to cover a basic idea, okay, how the CDT is used in actuator sizing and selection. So we'll touch on the surface level, we'll not go in deep. So once we have the CDT curve from the application, let's say, or you have the data of CDT, then what you can do is for your operating condition, you can calculate the torque, dynamic torque, okay, for each and every opening. So once this is done, then there are other torques, right? Like you add to this hydrodynamic torque, you add the seating torque, the packaging torque, and then the bearing friction torque. So all these torques you can add on the hydrodynamic torque. So what you get is a total opening and total closing torque. So you add them and subtract the dynamic torque, and then you add everything, then you get closing torque. So all those things. So you will get two basic curves, which is total opening and total closing. Okay. Now, what you need to do is you need to have the minimum required shaft torque. So you need to find what is the maximum of closing and opening for every one angle of opening. So you pick the maximum value out of all the openings. Okay. So that defines your MRST. So minimum required shaft torque. And then you to find out the actual sizing torque, then you multiply it with the factor. Okay. So that gives you the actual sizing torque. Now you take this valve, the actual sizing torque, which is MSRT multiplied by the factor, and then you plot the actual output torque, actuator output torque, and you make sure it should be even the minimum of the actuator output will be always above the curve, like the actual sizing torque which we defined, like which we calculated. Okay, so that is the minimum margin that should be maintained. Okay, so this is just a rough idea how you can use the CDT and do how it contributes to the actual actuator sizing and things. So now we'll go back to how what are the different methods with which the actuator or sorry the CDT or the dynamic torque is calculated. Okay, so first we'll start with the flow loop testing method. So what happens is like these flow labs, affiliated like certified flow labs, like FCRI in Kerala, India, and then Utah Water Research Laboratories. They follow certain standards like ANSI ISA 75.02.01 standards, which defines what should be the length of upstream pipe, downstream pipe, how this experimental flow loop test should be conducted. So it also defines where the pressure tapping should be in the upstream. For example, 2D, 2 times the diameter upstream and 6 times the diameter downstream. So you can see it here. Okay. So downstream. So pressure tappings, how where to place. So these kind of what are the typical flow conditions? It should not be turbulent. It should not be a cavitating region. So these guidelines are provided in this standards. Additionally, M49 standard guideline that provides how to measure this torque specifically. So you install strain gauges on the shaft torque that will give you the opening and closing torque. So once you have this value, then you can calculate the dynamic torque. Okay, for every opening for that flow condition. So using this dynamic torque, you can calculate the CDT. So before going into the challenges of the this particular method, I would want to I would like to touch on the new product development cycle, what happens, and then it'll be easy for us to discuss the further points. So let's say a typical new product development, what happens is there is a design requirement based on the market customer need or the competitor values and so on, so on. So we get the design requirement with a target flow performance. It could be CVN and CVT as well. So the design engineer, based on his experience and knowledge, so he designs the valve, and then the valve design goes to manufacturing, the prototype of that valve, and then it is transported to a remote facility where the lab is located, and then the lab conducts the flow loop test to provide us the report, which includes the CV and CDT curve. Okay, so typically this whole process, the flow loop test process takes weeks depending on the queue and a lot of things. But if I include manufacturing the prototype, design and manufacturing the prototype, the timeline goes haywire. So it goes in 2 to 3 months of time. Okay. So let's now look at the challenges in flow loop test. So what happens is limited flow insights. That is the one challenge in the flow loop test. What happens is in the flow loop test report, they provide the CV and CDT value. We get the CV and CDT value, but what is missing is what went wrong. Let's say you missed the target value, the CV or flow capacity or torque. It's not up to the target. So you need to redesign it. But on what basis, right? So where it went wrong, what is the scope of improvement? So that flow insight is missing from the flow loop test reports, where the visualization of flow separation or low pressure zones prone to cavitation. So those kind of insights are missing. And the design changes involves a lot of cost and time. Imagine you have to go through all of this whole cycle again if your first design is not performing well. So the third one is resource limitation. When you have large size valves, even the labs will have certain limitation to test the valve in its original size. Okay, so these are the challenges. So what are the other alternate methods available to flow loop test? She will come. Here is a comparison: analytical and numerical methods. So we are comparing it these on the basis of accuracy, time, cost, and skill required. So accuracy, in terms of accuracy, yes, flow loop test is the close. That's the truth, ground truth. Of course, with some conditions apply, there is some error involved, but that is the very close to ground truth. That is the thing. And analytical method, then accuracy is compromised, but the time factor and cost factor is considerably low. But the accuracy is not compromised. The skill is also not. And when it comes to numerical method, it goes very close to the flow loop test accuracy. Uh, and but the time and cost also it's reduced, but the skill required to operate the CFD software and achieve a meaningful result. Okay, so that is a bit challenge. So we'll see those. So challenges in analytical method, as I said, a lot of empirical relations are involved, and then it doesn't capture the complex flow phenomenon like turbulence, swirl, and local flow separation. What is the impact of a simple trim design change? So those things are not covered in the analytical method. Then comes the numerical methods, which is CFD. So CFD is nothing but it's like predicting the fluid flow or heat transfer, other flow phenomena, physics, by solving governing equations like numerical in a numerical method. Okay, so governing equations are Navier-Stokes equation. So that governs the flow. So to do that, it involves certain process. So you need to extract the fluid volume and then discretize the volume, the fluid geometry or fluid volume into some structured shapes, standard shapes called cells, okay, like here. Okay. So then the governing equations are solved in those mesh cells in a discretized way, like using numerical method. This is kind of a very diluted, simplified explanation of CFD. So that's not the intent of this particular webinar. So we'll just move on. So we'll see what are the steps involved in the conventional CFD approach. So as I said, the geometry starts with the CAD model. It needs a geometry. That is a starting point of a numerical method or CFD analysis. So we extract fluid volume. Fluid volume, it's nothing but the surfaces which comes in contact with the liquid. Okay, so it's a fluid. So that is the thing. So that's the fluid volume. It should be watertight, and then there are a lot of manual efforts are required in CAD cleanup and fluid volume extraction. Then comes the meshing part and the boundary conditions, numerical methods, setting up the numerical methods, selecting the right turbulence model. So all those things comes under the setup part. Then the computational part. So once the uh, pre pre-processing is done, this three steps comes under the pre-processing. Once this is done, then comes the solve part. So actually, you're in part of boundary conditions, and that comes on the solve. So you solve the CFD, like CFD using a CFD solver. You perform the simulations for this on this mesh and the setup on your local computer. So heavy computing uh, efforts are required, like computational resources are required to solve a CFD simulation. And then this is the post processing after processing. So you get the results in both qualitative and quantitative way. Okay. So in this case, the the challenges are the whole process is very skill oriented. Like you need special training and upskilling required for learning this CFD processes. Okay, so it's very manual intense, and also expertise is required to do all the processes to handle to bring the very good mesh quality, appropriate mesh quality, and to handle solve divergence and to extract a meaningful result out of the same thing. So to simply put, let's say you have the same software and same CAD model, input model, and same software is provided in the hands of two different engineers, one with experience and then one is new, and then there is a good chance that both will extract two different set of outputs. Okay, so you need experience and expertise to get the meaningful and reliable output out of a CFD simulation. And then the second challenge is HPC hardware, high power computing, and the software licensing cost is another thing, challenges. So what we thought was we wanted to overcome at Simulation Hub, we wanted to overcome these challenges and to support our mission, like which is to democratize this technology, and take it to the hands of design engineers. Okay, so we came up with Autonomous Valve CFD application, which is nothing but a virtual flow loop test, I would say. It mimics the actual flow loop testing process to extract, and because it follows all the ANSI ISA standard and M45, M49 manual, and to produce the results like CV, KV, CDT, and cavitation index. So what it is backed up by, like it's powered by Autodesk Platform Services for to upload the model and flow visualization purposes, and then AWS, Amazon Web Services for running the simulation, and the third one is the open form, like and wrapped up in Simulation Hub APIs. There are a lot of other APIs we have written on Simulation Hub platform. So how it works, the autonomous valve CFD application. So it needs very simple or minimum inputs. So starting from the CAD model and the flow direction, whether it is a shaft side flow or the seat side flow, and the opening conditions for which you want to simulate and obtain the results. So once these things are available, the app will provide you with the group of like a set of typical qualitative results, post-processing results like flow lines, velocity contours, surface pressure, and also the quantitative results, which is the main part, the CV curve, CDT curve, and head loss coefficient, cavitation index, all the performance, valve performance data, and then all combined in one consolidated report. So this gives you the complete CFD report, a typical conventional CFD report that you can hand over. So all these things happen autonomously. Okay, so user doesn't have to know the process of CFD or anything, and then the simulations runs on the cloud, AWS, right? So you don't need a local server or anything, local machines to run the simulation. So even your normal laptop will do. So this application supports all type of valves in both control and isolation and rotary and linear valve types. So with this, Akshay will take over on and walk you through the app demo. Akshay, over to you.
Thank you, Praveen. That was a very insightful discussion on the today's topic of hydrodynamic torque. I hope all our participants, attendees have got some insights into how this particular, you can say, parameter or a coefficient impacts their actuator sizing.
Yes.
And yeah, I'll just quickly share my screen. My screen is visible, right?
Yes. Yes.
Okay. So this is the dashboard of the platform AVC. we just start with creating a new simulation. So as Praveen said, the app supports all sorts of valves. It's divided into 4 steps. We'll start with the uploading of the CAD file. So as it is in line with today's topic, we have chosen a triple offset butterfly valve. And we just have to quickly specify the valve type, the trim type, the size, the pressure class, the valve roughness. Then the next step is to specify the moving parts. So we just select whatever the moving parts. So in this case, it would be the disc, it would be the shaft. And we select the axis of rotation, which is very intuitive. You just have to select the shaft and it will automatically get the axis of rotation. We apply the rated opening, which is it's a quarter ton valve, so it's 90°. We also specify the number of openings that we want, and it automatically populates all the openings, and you can even preview the valve motion. Then we move on to the next stage, that is the defining valve connections. So in this stage, you just select the upstream and downstream pipes so that the application knows the direction of the flow. And that's it. You're done with the setup part. Just submit the simulation. And all of the CFD related, you can say, workflows are autonomous. And you can track the progress of each of them as each of them is completed stage by stage. So once each stage, say the fluid volume stage, meshing stage, everything is completed, we have a look at the results. So the results contains qualitative data and quantitative data. So this is the quantitative data. You will have a tabular view of all the values. You will have a graphical representation of all the values. And we provide both gross and net values. So these become very important in ball valves. And since the tool is a CFD tool, it's powered by APS, and we can visualize all the contours, the streamlines. We can get very wonderful insights from these as well. We can see where the flow is accelerating, where it's stalling. We can choose velocity contour. We can even choose the pressure contour. We can see, okay, this is the region where there's a high pressure zone getting developed. On the backside, it's a low pressure zone. So it could be susceptible to some cavitation. Even features like the stoppers or the seat can impact the CV of the valve. And all of this is consolidated in a report. So all the quantitative data that we saw and all the qualitative data that we saw is compiled in a very brief report, which has all the tabular values, the graphical representation, the formulas, the contours, and even the appendix in which we mention the pressure tappings and other calculations. So that was about the workflow of the application. So we'll move on to the next part, which is the case study. So as Praveen showed us that how various parameters can impact the hydrodynamic torque coefficient, we did a small case study, and we, as CFD engineers, we also wanted to see how well CFD and AVC can mimic reality, because that's the point of CFD. And so we did a small case study in which we analyzed the impact of 3 parameters. It was the valve trim design, the flow direction, and the valve orientation. Quickly go through them. So this is just a visual representation what we are going to see in the further case studies. So case study 1 would be understanding the impact of eccentricity on the CDT or the hydrodynamic torque coefficient. Then it would be based on the flow direction. So is it shaft side? Is it seat side? and then how the valve is oriented at the end of an elbow bend. So let's look into detail regarding the parameter of eccentricity. So we have analyzed two cases. One is the centric butterfly valve, the other is a double offset butterfly valve, and this is how the CDT curve for both of them look like. So since you can see the centric butterfly valve has a very high torque at, let's say, 80% opening, 78, 80% opening, and it goes down to zero. So this is pretty obvious because at full opening, the fluid on the top of the, you can say, top side and the bottom side is, the profile is same. The forces are very well balanced, and the net torque acting on the valve at that opening is close to zero, as both the torques, the anti-clockwise and the clockwise torques, are balanced perfectly. In double offset valve, what happens is it reaches a certain maximum value near 60 degrees, 65, 62, 58 degrees of openings, and there will come a point where it becomes zero, but this is not at 90-degree opening, and this is precisely because of the design of the valve. Because what happens is there will come a point where it will go down, and that is because of the fact that after a certain angle of opening, in this case say 81 degree of opening, what happens is the fluid forces tend to overturn the valve, and this overturn is quantified as a valve opening. And since the sign convention says the torque that tend to open the valve are negative, we see a negative CDT. Moving on to the next parameter, that is the flow direction. So as Praveen had mentioned in the earlier slides as well, that flow direction plays a very important role in the CDT characteristics of the valve. So we will look at it in further detail. So shaft upstream and shaft downstream are the two cases considered here. So this is an offset valve, and this phenomenon, as we discussed in the previous slide as well, is observed in offset valves. So in shaft downstream, or you can say seat side configuration of the valve, what happens is at the initial openings, the fluid forces will tend to close the valve, and there will come a point where the forces are unbalanced and they tend to overturn the valve, and this overturning is categorized as opening of the valve, which gives us a negative CDT. In the shaft upstream condition, or the shaft side flow direction, what happens is it reaches a maximum value near, let's say, 75, 78% of opening, and let's say even if the valve tends to overturn, the area on this side of the valve is larger as compared to this, and it will again try to close the valve. Hence we see the CDT to be positive. Moving on to the next case study, that was based on the orientation after the elbow bend. So here we have considered three orientations, and this is a consolidated view of the CDT curves for all of the three configurations. We'll look into detail how each one of them is getting simulated. So we'll start with the configuration 1. In this configuration, what happens is, due to the bend, the portion that is pointed by my mouse pointer here, or you can say the right side of the pipe in the downstream direction, has a higher magnitude of velocity, and the left side has a lower magnitude of velocity because of the existence of the bend. When the valve is at, let's say, 80 degrees and it is trying to overturn, due to the high velocity, the valve will again be rotated so as to close the valve. Hence, we observe that the CDT is positive. In configuration 2, we see again torque reversal, and this can be explained very easily as the magnitude here, where my mouse is pointing at the moment, the magnitude here of the velocity is very high as or higher as compared to the other side, and this tends to overturn the valve. Due to the overturning, the valve is characterized as opening, which is a negative torque, and hence the CDT is negative here. In configuration 3, we have axis in the vertical direction, and it's almost like the valve is slicing through the velocity profile at full opening. So the forces are balanced completely in the, you can say, the right side and the left side of the valve. And since they are balanced, the CDT at 90 degree of opening gives a balanced torque, meaning the anti-clockwise and clockwise torque is well balanced, and it gives us a CDT of 0. So in all of the three cases, we have considered that the pressure drop across the valve is 1 bar, and this is all of the cases in action at the same time. So that brings us to a validation study. So you might have a doubt, or as CFD engineers, we need to validate our solvers, we need to validate our application. So a genuine question is, have you validated it? The answer is yes. We have worked with FCRI, and we have done testing with Utah Water Research Laboratories as well. And we found out that the application is able to give a more than 90% accuracy across various types of valves, various trim types, and various sizes of the valves as well. So you can observe here, so from CV1 to CV over 100,000 or even a million, 100,000, we are, in the range of 95% accurate. Obviously, there are a few outliers, but overall, the pattern, or the, let's say, the accuracy is 90%. From CFD point of view, this is very good. Even from FCRI testing, they always give you a tolerance for their measurement, you can say, instruments. So even in that case, CFD is good to go. So I'll hand it over to Praveen, and he can explain you in detail what actually happens behind the scenes.
Sure. Thanks, Akshay, for running through this interesting case studies. Akshay, just wanted to confirm my audio and the screen sharing is fine, right?
Yes.
Okay, great, thanks. And okay, I guess the validation study is already covered. So I'll jump to what happens behind the scenes, right? So I'll tell you one interesting fact. For Akshay to bring all those interesting case studies, so all it took for him is 1 to 2 hours of time to bring all the results of all the case studies, whatever you have seen so far. So how was it possible, right? So to answer that, we need to see what happens behind the scene. So what we follow as a standards, right? Like there are multiple standards for formulas and test procedures, and the procedures specific to cavitation, as well as the torque M49 standards, as well as verification and validation standards for CFD simulations. So all these things are referred and used in the application process. And then CAD cleanup is done autonomously. The algorithm identifies which gaps to be closed and it processes the cat cleanup very effectively. So and then the mesh generation, it happens very seamlessly. Like it identifies it targets both to capture the geometrical shapes as well as the flow gradient, like where the flow is supposed to have some gradient, like the velocity, flow separation. So those kind of things are captured. So to do that, you can see the mesh size variation. So it starts from a little bit coarser, and then it goes fine, and then fine, and very fine near the surface or edges of the valve. And then on top of it, to capture the boundary layer phenomena, it has prism layers as well. Okay, on the valve. And then we follow all the standards like 2D, where to measure the upstream pressure and downstream pressure, to make sure the flow is fully turbulent, and convergence check, residual convergence, pressure monitor, it should be flat. Along with the on top of residual convergence, we also monitor pressure and CV. So all these things are happening, and also there is a Y plus alert. So whenever the mesh is not able to, meet the Y plus criteria demanded by the selected turbulence model, then the Y plus alert is created, and then the meshing is again refined, and then rerun. The simulation is rerun. Okay, so these things are implemented in the app. So now all these process, whatever I've shown, cat cleanup and everything, meshing and solve, happens on the cloud. And for every opening, there is a dedicated 36 core machine assigned on Amazon EC2 instance. Okay. So under the results is fetched and shown in your browser, and CV, CVT values are provided. So this is not for one opening. It happens parallelly for all the angle of opening. So fully closed to fully open. So all angle of opening runs parallelly. A dedicated machine is assigned, and the simulation doesn't go in queue. It runs parallelly. So at the end of 1 hour, 1.5 hours, you will get the complete summary of with report and the complete curve. Okay. So that's how it is possible. It's not just that. You can have, let's say you have multiple design options like what Akshay did in the case study, configuration 1, 2, or 3. So all those things can be run parallel at the same time. So you can do the same simulations in the same login, because everything is independent and has its own dedicated machines for all the CFD process. So at then you will have all the CV curves and CVT curves with the report and everything. So it's a seamless collaboration across teams, working in different geographical locations as well as working in different product lines. So they can collaborate on the product, like it's a cloud application. So it's very seamless. So in comparison, the conventional method relies more on expertise and manual process, in-house resources that puts us a limit, and it takes more time in terms of weeks, days to weeks. And then in comparison with that, simulation hub is mostly autonomous process, and it's a expandable cloud computing resource, and the results are available to you in hours. Okay. So I often take this metaphor, as in to explain. So comparison between generic CFD and the valve CFD, autonomous valve CFD. So when you want to dig a small pit in your garden to plant some saplings, so what would you choose? A JCB machine, a big machine, or some simple tool specifically made for gardening? So this is specific tool. So generic CFD has a lot of informations and lot of features, models, and everything, but it's very hard to it can run even aerospace aerodynamic simulations, a flight. You can simulate a flight, also pipe with a generic safety. But valve specific, for valves, you need a valve specific fine-tuned autonomous CFD. Okay, that makes your job very easy, right? So even designers could do the things. So we'll see some real life customer success story, how they have applied this app in their process. So these are our list of customers across the globe. So including Bray, flow management industry from Argentina, and then Delval, Magwin, Interval. So all customers are listed here. And then last week we saw the success story of Bray. How what are the challenges? They had their generic CFD tool already in place, and their flow loop tests used to take 3 to 4 months, and then generic CFD takes 5 days. And how our solution reduced that 5 days of time into 1 hour and increased the number of CFD engineers or CFD usage. Design engineers they themselves adapted and all those stories. So this was done last week. So this is like some testimonial from Vrindesh Dua from Bray. So this week we'll discuss one such story from Delval. So Delval, when we started our association with Delval, they had it started with 2D drawings. So complete digital transformation of a Indian valve manufacturer. We have been constantly involved in that journey from the start. So they adapted to 3D CAD model, and then the simulation part. They started with 300 valve simulations in a year, and then now it's grown up to 1500 valve simulation. And they have been big contracts using simulation, and they got an edge over the other competitors. So, for example, they also use our tool for large size valve simulations. So, and then this is one of the case, very interesting case. So where they had a target CV of above 1,20,000, and they were getting 93,000. So we got a call in the morning, and then we with our technical support team and their engineer sat together over a call, and then we discussed all the possible. We analyzed the results of time, and then we discussed all the possible design changes that could bring or reduce the pressure loss or flow separation part. And then we arrived at one design which really gave them the required design CV. So all this happened over a time span of 3 hours. So that's the interesting case study. And then again another case is like Magwin. Magwin, we were a simulation partner to launch a large size plunger valve in their portfolio. So lot of things. So we'll see much more in the future things. So what's next? There is a trial subscription available. You can go to our website and register for trial subscription. You'll get 15. Usually the trial subscription is for 15 days, and you get 20 simulation credits. You can do simulations of 20 valve openings. Okay. Or for our webinar attendees, registered users, they can schedule a call with our expert using a request demo button on our website. We'll share the link, and you can obtain claim a big discount in both the subscription, the extended period of subscription with 1 month and 30 simulation credits, and some exclusive discount for our webinar attendees. So for the subscription options, okay. So what's next is the cavitation index prediction. So next week we'll be discussing more on how to calculate cavitation index, and some case studies. With some case studies, will bring you some interesting case studies, and even we'll share some insights from our research work we presented in Valve World, Germany. So even our technical article got published in Valve World magazine this week, August issue, which was focused on severe service control valves. So our article is presented. So same research work will explain in detail during the next webinar. So with that, that brings to our end of this session, and the contact and everything you can connect with us, and the session is open for Q&A. Akshay, do you see any questions?
I am
Typically,
unable to see it.
yeah,
Sorry.
I guess, yeah. Typically, what happens is like one of the questions is like, how do we handle very complex geometries or complex CAD features, especially when it comes to, anti-cavity trims and stuff. So I just kept this slides for reference. So what we have added new features like, mesh refinement features, local mesh refinement features that will provide you um, uh, options to resolve the trim holes and like anti-cavity trim holes also. So much complex geometries like additive manufacturing designs. So those can also be simulated using the application. Of course, the time will vary depending on the complexity of the valve. Okay. So I guess we are almost near the end of this session. You can post your questions on the chat window as well as uh, yeah, I see some more question about the CFD. I guess there is some question from CFD side. What turbulence models and stuff. So as we show already, the realizable Cape's law and turbulence model is what we use, and we observe that works best for the most of the sizes and types. And we also find the algorithm also fine tunes depending on the size. Very small size will have a different model and things. But what happens is like, let's say your organization already follows certain SOPs and you have a certain turbulence model or mesh size and everything. What we can do is we have a advanced user mode that can be enabled. Okay. So autonomous mode and advanced user mode. So for advanced user, you have the full control about the sizing as well as the turbulence models and numerical schemes. So there you can have a full control. So you can follow your organization standards and make it as a template for your user set of users in the organization. So that answers it. Okay. Okay, and another question about the data part. So the data is completely secured. We follow all the procedures for AWS specified processes to store the data on the cloud, and then it's kind of banking grade security. So your even the technical support doesn't have access to your data unless you raise a ticket. So that to resolve the ticket and then it's done. So those data is completely secure and that can be taken care of. That is taken care. Okay, I guess we are nearing the end. So
There is one question.
okay,
The CDT will vary for open and closing, especially for butterfly walls. Did you done any case study for CDT capturing of open as well as closing of the wall?
okay. So that's completely new for me. Like because the closing torque, the total closing torque and opening torque that will vary, but the CDT value remains constant for the well, that's what even the standards M49 reference says. But I guess this question is from Muthukumar. We can
Yes.
connect personally to understand if there is some requirement specific to that. We can take that and resolve that as well. But in my understanding, I guess the CDT remains constant. So even the closing and thing, no, I guess. But yeah, I would like to connect and explore more on that aspect. It's an interesting thing. Yeah.
Just from an initial guess, I could say the pattern would be kind of a mirror image, but the values might be,
Yeah, pattern is like kind of the reverse of
yeah,
things, but yeah, values. But it's an interesting thing.
it's
We'd
an
like
interesting
to
question.
we'll write to you separately and arrange a call to understand the requirement and things. Thanks, Muthukumar, for bringing that question.
There's another question.
Yeah, yeah.
Uh, so, is it sufficient? So, are steady state simulations sufficient to predict torque, or do we need transient simulations for it?
Okay, steady state simulation are very well sufficient for the CVT values taught. I understand, and if there is a bend or some flow phenomena can create that fluttering effect in the butterfly valves. But if your interest is not to capture those, and just, to understand if there is a offset to the expected value of torque, then what is the reason that steady state simulation is sufficient? So based on that, you can optimize the design and avoid the fluttering effect and things. So when there is a involvement of water hammer and other stuff, but for torque, I guess it's steady state is very well sufficient to capture. I think there are a few more questions. I guess we can take those separately. We'll answer through email. But thanks for joining, and then your continuous support in this is the second week, and we request you to join for the third week as well, where we'll be discussing more interesting case studies like with respect to cavitation part. So stay tuned and yeah, thanks. See you next week. Excited for it. Thanks, Akshay, for joining. And yeah,
Thank you, Praveen.
have a
Thank you,
wonderful
everyone.
day ahead. And see you next week.
Bye bye.